All right, guys, so now what we're going to do is we're going to start looking at magnetic fields. All right. Now, I want to show you a couple of things. First thing we're going to start off with, this is, of course, a normal everyday magnet. I've got here a compass. Okay, now a compass normally points the direction north. And so you'll see right now the red is pointing towards north. North is generally in that direction. All right. Now, when I put it near my magnet, what happens? Well, you'll see that it actually points away from north. So the first thing that we learned is that the North Pole of the Earth is not actually the same thing as the North Pole of a magnet. The North Pole of the Earth is the same thing as the South Pole of a magnet. But when we start to look at this, we're going to say, okay, well, the red direction points in the direction of the field. All right. So on Earth, we say that the field, the magnetic field of the Earth points towards the North Pole, right? The North Pole of the Earth. It's not a North magnetic pole, it's just the North Pole of the Earth. Okay, so for example, at this point, we could say that it's going up and, down and to the right here, okay? If I place my compass at a different place, you can see that it's pointing in a slightly different direction. It's pointing out this direction. If I put it closer here to the middle, you can see that it's pointing in the left direction. Okay, and as we kind of move around, you can see, always looking at which direction the red is pointing in, right? You can kind of get an idea of what the pole looks like. What the magnetic field looks like. All of these arrows that I'm drawing, all of these vectors represent the direction that the magnetic field is going at this specific moment in time. And you can get an idea that it's going away from the North Pole and it's going towards the South Pole, right? And so that's kind of the first thing that we want to recognize, is that when we talk about magnetic fields, it goes away from the north and towards the south. Now, this is very similar. If I took the magnet away for a second, this is very similar to if I had a positive charge here and a negative charge down here, right? The field would go away from the positive and then it would go in towards the negative, right? And that's the exact same thing that we get inside of a magnet, is that a magnet will go out, it'll go around, and then it will go in, just like this. Same thing up here, it'll go out, it'll go around, and it'll go in, just like that. Depending on where we start, we should be able to get a similar process, something like this. And then down here, we go out, around, and in. All right, same thing here, out. Eventually, we would expect that it would curve around one way or the other, and then in. And so there's kind of an idea of what your magnetic field looks like, out of the north, in towards the south. Okay, now unlike your charges, right, in the charges, it would also go from here to there. But that's not how it works inside of a magnet, because a magnetic field completes a circuit. It goes in a circle. And so as it goes into the south, within the magnet, it actually goes this direction. Okay, and so each of your magnetic fields is a loop. Now, one of the questions is, well, where does that magnetic field come from? You know that all atoms are made up of a nucleus and electrons. What you may not know is that the electrons inside of that atom are spinning. They're moving around and spinning. The direction of the spin of the electron determines the magnetic field. If all of the electrons are spinning in the same or similar directions, then you tend to get a magnetic field in one direction or the other. Now, because it's spinning, for example, like this, if it's spinning like this, you're going to get a north that's in one direction, a north magnetic pole in one direction, because from one direction, it looks like I'm going, let's see, what would that be? That would be counterclockwise. And then if I look from the other direction, for example, if I turn it around and go in the same direction, it's now going clockwise, which means on the other end, I'm going to get a south pole. All right, and it all depends on how those electrons are spinning around inside your atoms. All right, if you have the same number spinning one way and the same number spinning the other way, they tend to kind of cancel each other out. Now, some metals, you can get those electrons to change the direction that they're spinning, and you can make them be magnetic for a period of time. Some objects, some types of material don't do that. That's why even when you get close to something magnetic, sometimes things don't stick up. It's only certain things that can be magnetized so that you can get the atoms to rearrange themselves, the electrons to spin themselves in a certain way to kind of create that magnetism. All right. Another thing I want to show you here, come on back to the table, is this. Okay, so you'll notice here, this is just a clear piece of plastic here. On top of it, I've put some iron filings, so just little pieces of iron there. If I take a magnet, this is a pretty strong magnet here, not super duper strong, but it is pretty strong. If I place that under the iron filings, look at that. You'll notice that they automatically arrange themselves in that field, right? You can see some of them here. They're going around like that. On the outside, you can see them kind of bending around in this way. So you can see how they rearrange themselves in the direction of the field, all right? So the iron filings, because of the way that the electrons are spinning in there, will reorient themselves to match the magnetic field. All right. Now, very similar to how when we looked at positives and negatives, when the field was going the same direction, those objects were attracted to each other, right? When we had a negative and a positive where everything was coming into the negative like this, right? And this is just a quick sketch. And then a positive, everything going away from the positive, right? When the fields were going the same direction there, they were attracted together. It's the same thing when we look at magnets, okay? If I take two magnets and I take a north and a south, where it's coming out of the north, into the south, out of the north, into the south, because here it's coming out of the north and here it's going into the south, we get an attraction, and they're attracted together because of the fields going in the same direction there. Similarly, if I were to put the north and the north together, they would repel each other. They would try to push each other away, just like two positives would try to push each other away. All right, if I take this magnet right here, this red magnet, let me take some more compasses here. What do you notice? What do you notice? Well, hopefully you see that the field is coming away, right? The compasses, the red of the compass is showing you the direction of the field. It's going away from this side and in to that side, right? All the reds are pointing in this way. All the reds are pointing away from this one, right? Now, often people say, can I split it in half so that I have a north magnet and a south magnet? And no, that doesn't work, because remember, it goes all the way down to the atomic structure. And even in the atomic structure, each atom will have a north and a south. So even if I chop this in half, I'm still going to have a north and south and a north and south. In fact, I did drop this one the other day, and I broke it into two pieces quite accidentally. But look at this. So we still see that it's coming out of this guy, but it's coming into this end now. And then from this end, if I separate a little bit further, you can see that it's coming out of this one and into that side. And so what used to be one single north-south is now north-south, north because it's going away, and south because it's going in. And so I've taken that one magnet that had a north and a south, and I've turned it into two magnets. All right. I can put this in the middle. Notice that it does exactly what I expect. The field goes out of the north and into the south. So look at that. When they're about the same distance apart, see, it doesn't really want to come towards this one because it should be coming out of here, but it should be coming out of here. So it doesn't point towards either of them because at this point, the fields would be going up like that. If I were to move it down here, the fields would be going down like that. So we can see that when it's down here, the fields kind of bend this way. And when I'm above, the fields kind of bend in this way. All right, so there you go. Right in the middle, he's kind of confused, but when I'm above that half line or below that half line, the fields know exactly where they want to go, and you can get an idea of what the fields would look like when they're opposing. And so again, that's where we would get that they don't really want to be together, that they would repel from each other. All right, so that's an introduction to fields. Watch the next video because it's going to start connecting fields and electricity, right? We talked about the fact that it's the spinning, the moving electrons that create the magnetic field that make these magnets magnets. Well, we're about to go a lot deeper than that. All right, come with me in the next video. See you there.